Welcome back. So in this week's tutorial, we will be discussing some of the practical applications of point group so far what we have learned. So let us see some of the kind of questions which try to change the words so that the question appears very difficult, but then what is the approach to solve such kind of questions? Okay. So let us and we'll try to work out at least four questions of different types. So let's see. The first one is, what are the highest order rotational subgroups of following point groups? So question is asking that what are the highest order rotational subgroups? So subgroup, as you know, is the set of group elements which follow all four properties of that particular of the group out of that particular point group, right? So let's say if we have C6H, okay, so now we should know how to find out what are the symmetry elements or symmetry operations present. So let me just list down for C6H. I have written it here with me. So you have E, C6, C3, C2. These are all the group elements or symmetry operations. C3 square, C6 5. Each of this is a different class. Then we have S3 5, S6 5, sigma H, S6, S3. So these are the set of elements. Now it is saying that what is the highest order rotational subgroup. So for rotational subgroup, you have to consider the rotational elements only. So which is pure rotational axis, that is C6. So C6 is the highest order axis. So let us see if we generate all the operations from C6, do we get a subgroup out of this? So that will be E, C6, C6 square, C6 cube, C6 4, C6 5, and C6 6 will be E. So now this is equivalent to C6, right? Then this will be C3. So we have C3 here. Now this will be C2. We have C2 here. This will be C3 square. We have C3 square here. And this will be C6 5, right? So these are the elements which contain only rotation, pure rotation. So we wanted to see if the pure rotational subgroup is present. So yes, a subset is present. We don't know whether it is subgroup or not. So let us see. So if we look at just these six elements, this actually forms a point group for the cyclic group C6, right? So if we look at C6 point group, then that is composed of only these elements. So E, C6, C3, C2, C3 square, and C6 5. So we can directly say that yes, this is a C6 is a highest order rotational subgroup of C6H, right? So that was easy. So you can, so idea is you have to find out only the elements which composed of rotational operations and then see whether it is forming. So in this case, we already know that it's forming a C6 point group, but ideally you should be testing it for all four group properties, that all four group properties like closure, associativity, inverse, and identity, all four are conforming to this set of elements. So then we can say that C6 is the highest order rotational subgroup. Okay, so let us look at another one. So we have D2D here. So now what are the elements present or the group this thing present? D2D will be symmetry operations will be E 2s4, and we have C2 and 2c2 prime and 2 sigma d's, right? So now we are only interested in the rotational things, right? So this is not rotational, this is reflection, this is rotation and reflection. We only want the rotations, right? So the rotational subgroup will be E C2, C2 prime, and we can call it a C2 double prime, or we can call two C2s here. So basically, three C2s which are perpendicular to each other. That is our subset. Now, this subset, does it belong to a particular point group or not? We have to identify. So if we look at, yes, it does belong to. So the point group is D2 here. Let me just also look at the literature. Yes. So if we say that this belongs to D2 point group, and thus we can say this is the highest order rotational subgroup of D2D. So D2 is highest order rotational subgroup of D2D, right? So I'm just saying D2 is a subset of D2D. Okay. So where subset is meaning highest order rotational subgroup. Okay. So I hope this is clear. This is a kind of questions which is sometimes asked in different type of exams. So I thought it will be interesting to cover this. C5, let's say C5V, not C5H. C5V. So now C5V, what are the group elements under C5V? We have E, 2C5. So two operations given by C5, two operations given by C5 square, and 5 sigma V's, right? Now, what is the highest order rotational subgroup? So we cannot consider this one. So we have E. If we consider the operations generated by C5 now, so this will be C5, C5 square, C5 cube, C5 4, right? These are the operations that will be generated. So are these following any point group? Yes. So this will be a C5 point group, right? But do we have all the elements which are present here in this? So now that again we can test by looking at if all of these elements, all of these, do they conform to the associativity closure and all the properties. So individually we have to work it out, pick up any example and start working on it. Or else what you can also do is, when you're testing these properties, you can take the matrix representation of each symmetry operation and use that to test various properties of the group. So once you do the matrix representation, you don't have to imagine a molecule and do all the operations to find out the property. So take XYZ as the basis, create a matrix representation for all of this, and find out whether if all these are following the properties of the group or not, right? So this is one type of questions. So let us look at another type, which is actually little difficult, not difficult, but you need little imagination. So now say, what is the point group obtained by adding, deleting given operation? So let's say you're given a point group. Let's say you're given a C3 point group. Okay. And now to that CH3 point group, let me write down point group. C3 point group. To this C3 point group, you are adding a inversion operation. Okay. So what is the new point group? How do you find out this? So there can be enormous number of combinations. I've just taken one example here, but you can have different type of examples. So how do you approach? What is the approach? If you know the approach, you can solve any given problem, right? So, but you should know the approach for these kind of problems. So for C3 point group, what you have is list down the elements, group elements. So you have E, C3, C3 square, right? And on top of that, you're now adding I. Now adding I is not just adding I. So if you add I to this, what additional elements are also added, that one has to identify. Okay. So how do you identify that? So the very easy thing is that group always follows closure property, right? Group follows closure property. So that means what you have to do is you have to create the products of different elements and see what is the resultant which you are getting. Now that resultant may belong to the already existing element or may give you some additional element, right? Okay. So for example, if we do C3 into I or I into C3, what do we get? Let's say if we get a new operation. So now that new operation can come here. So how to do that? Let us see. So again, the easy way is to write down the matrix representation for the two, because you don't know how the molecule will change. Let's say if we have C3, some molecule which is of C3 point group. Now, if we are adding I operation, how do we change the molecule? What is the symmetry of the new molecule? That is impossible to predict. So best way is to find out the matrix representation. Find out the matrix representation of each of the elements and keep finding the products or squares of different elements, because that is bound to give you new element unless all the elements are completed, all the elements of the new group are completed. So let us see how does it work out. So for C3 and I, for C3 we have learned that the matrix representation can be written as minus half minus root 3 by 2 0 root 3 by 2 minus half 0 0 0 1, right? And for I, matrix representation can be written as minus 1 0 0 0 minus 1 0 0 0 minus 1. Okay. Now if I do C3 into I, what do I get? So it's a unit matrix with negative sign, so multiplication is easy. So all you have to do is just change the signs over here, right? So that means I will get half minus root 3 by 2 0 root 3 by 2 half 0 0 0 minus 1. Okay. Now what kind of a symmetry operation is this? So if you want to define this matrix representation as a single symmetry operation, what kind of operation is this? Now first of all, it is not a pure rotational operation. Why it is not a pure rotational operation? Because a pure rotational operation would never give you minus 1 in the z, right? Minus 1 corresponding to the z basis. So that means if Z is getting converted to minus Z, that means there is a reflection involved. So it has to be a rotation and reflection, right? So now rotation and reflection means that this is some sort of a rotation XY. Now what is that angle? That angle we can identify by looking at the value. So if we have cos theta is equal to half, we have theta is equal to, you can say 60 degree, right? So that means this is, if my n will be 360 by 60, so this will be 6. So that means this will be a C6 kind of rotation, right? This was C3 rotation, this is C6 rotation now. Now if this is C6 rotation and this is sigma h corresponding to it, so this would become S6, right? So now what you have obtained is you have gone to little higher number of elements. So you have obtained S6. Now S6, if you calculate the square of it, so that will be S6 square. What else do we have? Yeah, S6 square. So that will be C3. S64 will be C3 square. So what you will have is S65, which will be the independent operation, right? Now S65 will also come as a product of one of these. Maybe it will be from I to C3 square or so on and so forth. Now this follows all the group properties. Of course, you have to test it. I'm not testing it here. I'm just telling you, once you have identified S6, you know that S6 alone would give you S6 as well as S65. So I have included this operation here. But what you have to do is you have to test the set of group elements for closure. First of all, closure property, and then associativity. So once the closure property is fulfilled, then only you can go for test for associativity, inverse, and identity. Okay, so these four properties have to be fulfilled, and then you can say that now the new group is nothing but S6 point group. Okay, so from C3, by just adding one symmetry element, you have gone to S6 point group. Okay, so that otherwise it is difficult to imagine that what will be the point group by deletion or addition of a symmetry element. So same thing can be done by addition or for deletion of element also. So again, this is an important question. I've seen this coming in different exams, so that's why I thought I'll bring it up here. So now let's ask, third question is, what is the group of operations which are generated by Sn if n is even or n is odd? Okay, so let us take each of this case with example. So let's say if n is even. Okay, so let's consider S4. So n is even. So now what are the operations that will be generated? So S4 will generate S4, S4 square, S4 cube, S4 4. Now each of this is called as C4 sigma, right? So this is an independent operation, so we'll keep it as S4. Now this will be C4 square, sigma square is E, so this is nothing but C4 square, and this can be then written as C2. Okay, S4 cube can be written as C4 cube and sigma cube, so you can simplify it as C4 cube into sigma, so nothing can be, so you cannot simplify it further, so S4 cube will be there. S4 to the power 4 will be C4 to the power 4 and sigma to the power 4. Both are E. So you have E. So generating operations from S4, you get 4 different group elements, right? Which is E, S4, C2, S4 cube. Now these are the set of elements which will form S2 or S4 point group, right? So that is easy to identify. So for n equal to even, if we are generating operations of S4, you will get S4 point group back, right? Now let us say for n equal to odd, what is the case? So let's consider a simple case of 3 because 5 will be too long. So n equal to odd. So let's say what are the operations which are generating S3, S3 to the power 2, S3 to the power 3, S3. So we have to keep going till we hit E, right? So let's say if we have already hit E at S3 to the power 3 or not. Okay. So S3 will be equal to C3 sigma, so which is nothing but S3 again. This will be C3 square sigma square. So sigma square is E, so you can write it as C3 square. S3 cube will be C3 cube and sigma cube. So you will have, this is C3 cube is E and sigma square is E. So you're left with 1 sigma. So you have 1 sigma over here. And what else we have? So you are still not got E. So we have to keep going. S3 to the power 4 will be C3 to the power 4 and sigma to the power 4. Now sigma to the power 4 is E and this is C3 to the power cube is E. So you are left with 1 C3 operation. So again, we are not getting E. So move further. So this is C3 to the power 5 and sigma to the power 5. Nothing will go to E. So you are left with C3 square and sigma square. So that would mean you have S35 back. S3 to the power 6. You have C3 to the power 6, sigma to the power 6, which is E. So after that, you don't need to generate more operations because that will give you S3 again. Okay. Now, so what we have got is E, S3, C3 square, sigma, C3, S3, 5. These are the set of operations which we have got. Now this set of operations, what is the point group for this? This will give you C3H point group. Okay. So that means if we are generating operations using S3 axis or Sn axis where n is equal to odd, then we will generate CNH point group. Okay. So in general, we can say Sn will give you CNH point group. So operations of Sn where n is odd, for odd n will give you CNH. Although it appears that it's a S3 axis only, then but still it pops out sigma out of nowhere, pure rotational elements out of nowhere. By just doing operations of S3, you're getting a CNH point group. So these are also kind of questions which are asked in different type of exams. So it is important to cover this. Okay. Let's look at one last question and then we can stop for today. So let's see. So the fourth question is express operations generated by S5 and S8 in conventional notations. So now this is easy, right? Now that you have learned how to generate different operations of S5, so basically here they have taken two examples where n is odd and n is even. So for even n, you have to keep going up to raise, so S8 to the power of 8, and for S5 you have to go up to the power of 10. So why I'm saying that, let's just look at it again. So operations of S5. So what all operations S5 will generate, and you have to put it in conventional notation. What is the conventional notation? So S5, S5 square, S5 cube, S5 4, S5 5, S5 6, S5 7, S5 8, S5 9, S5 10. We have earlier seen that only when we hit S5 up to or Sn raised to the power 2n, we will hit E, otherwise we will not hit E. So we have to keep going at least up to the 2n part. So S5 is nothing but S5. So there is no change in conventional notation. What is S5 square? So we have C5 square into sigma square. Now sigma square is E, so we can write it as C5 square. Okay. So although it is C5 square, but it is a operation generated by S5. So this is what it means by conventional notation. Now again, C5 cube, sigma cube. So this does not conform to anything. So we'll keep it as S5 cube only. Again, this will be C5 to the power 4, sigma to the power 4. This is cancelled. So we will be left with C5 to the power 4, C5 to the power 5, sigma to the power 5. So we are left with only sigma. Okay. And so on and so forth. So now you can actually calculate, right? So these are the conventional notations for the operations generated by CS5. Similarly, we can work out operations of S8 in the same manner. So here we have to go to 8. S8 to the power 2, S8 to the power 3, S8 to the power 4, S8 to the power 5, S8 to the power 6, S8 to the power 7, S8 to the power 8. Okay. So this will give you, and then you can figure out whether it will be S8 or C8 or sigma and so on and so forth, or E, right? So that's how you can generate different operations by rotation reflection axis and find out the corresponding conventional notations. So we have learned today how to work with different type of problems related to point groups, which can be subgroup or related to multiplication tables when we are trying to find the closure property and so on and so forth, right? So that is all for today. So next, let us see what is there for next class, and we'll come back with next week's tutorial.